Hello everybody. So as I'm making this video, we just had a test and we're moving on to a new topic and some new material. And so this video is what's going to get all that started. Okay, so most of what we do from now until our next test is going to come down to the concepts that are presented in this video right here. Okay, so to get that started, the topic will be about increasing versus decreasing functions in critical numbers, and I'll explain, of course, what all that is as we go along. Now, I wanted to start it very simple, okay? And so I have a function right here. F of x is x squared minus 8x plus 19. That's a fairly simple function, okay? We may refer to that as a function. We may refer to that as a curve. Most of what we're going to do from now until our next test is has a visual component to it. We'll talk about graphs, and we'll talk about the nature of graphs and what features they have and so on. And mathematicians and people that use math to do things often talk about for example, the nature of the supply curve or the demand curve, okay? And talk about supply and demand or whatever they want to talk about in terms of the properties that the curve or graph has, okay? So we might refer to formulas like this as functions. We may refer to them as curves, but those terms we could think of are interchangeable at this point, okay? All right, now, so I made a table here, and these numbers are really just arbitrary that I chose on the table. I've got x in this column and I've got y in this other column with respect to this function. And there's nothing special about my numbers. I'm just trying to illustrate something about the function. But I chose that x is -1, 0, 1, 2, all the way to 8. I did the calculations putting these values of x into my function, and here are the values of y that I got. Now, I want to notice if there's a pattern. I want to ask you, do you see a pattern? Maybe there's not that much of a pattern between the number 28 and 19 and 12, but the global pattern is that the y values are getting smaller up to here, up until you get to 3. 28, 19, 12, 7, 4, 3, they're getting smaller. So when we say a function is decreasing, that's what we mean. It means that as x gets bigger, y gets smaller. Okay, so think of it that way. X up, y down. All right, pretty simple. Now, once I get to 3, I notice the pattern changes. I get 3, 4, 7, 12, 19. Well, then the y values are getting bigger. We'll refer to that as increasing. Okay, so hopefully that's not too complicated. Do you see what I mean by the terms increasing and decreasing? Maybe some of the functions that we see will be complicated, but I guess the concepts of an increasing function or decreasing function, not too mysterious. But increasing, okay, that will mean that x is going up and y is also going up. Now, this is in my table. The table is just numbers. You see the raw numbers, the x's and y's, and whatever patterns you can identify. Now, we can also draw graphs. I can plot all these points, see what kind of pattern they make, and draw the graph. The graph of this particular function happens to be a parabola. It looks something like that. It's got this point 4 for x, 3 for y, down at the bottom. And it looks like this otherwise. So we might say that, okay, well, I can apply the concepts of increasing and decreasing visually to a graph. See how the curve is going down from left to right here, where it's decreasing, and it's going up from left to right here. That's where it's increasing, okay? Now, we'll also use intervals to express this. So we might say this function is decreasing on the interval from -infinity to 4, okay? So that may be the way that we express it. Here I'm just pointing to things and I'm saying getting smaller, getting bigger, but to report on that, I'll give an interval. So this thing right here, this is called an interval, okay? And it just means that on the x-axis from negative infinity to 4, you'll find that the curve is falling, okay? Decreasing, going down from left to right. It's increasing on the interval from 4 to infinity, okay? Because this curve rises, and it rises forever as you go to the right. All right, so all along the x-axis from 4 to forever, you'll find that the curve is rising from left to right, increasing. Okay, so that's how we're gonna think about the concept. Now that's part one. That's just preliminary information on what decreasing and increasing mean, okay? So part two, what role does the derivative play in this? So in our last test, for all that material, we learned how to calculate the derivative of a function. So there is such a thing as a function, and there's such a thing as its derivative, okay? And the way that we had thought about it originally is that I might use a symbol f of x for a function, okay? A curve, whatever you want to call it. And then f prime of x is the symbol I use for the derivative. And what does the derivative tell us about the function or curve? Well, it tells us how y and x change together. There's a big story about all the stuff the derivative tells us, but you know, in the function, if x changes, y will change as a result. The derivative tells you how the variables are changing together. So the function tells you what is y when we know x, and the derivative tells you if x changes, how does y change? That's a like very simple description of the function and versus the derivative. We could make it more complicated than that, but I'll do. But I guess if we're going to talk about graphs and whether a function is increasing or decreasing, that it would also be worth mentioning that the derivative also tells us the slope of the curve. If you imagine the original function as a graph, or you want to see it that way, the derivative tells you the slope of the curve at whatever point you want to look. Okay, you might find that on a curve it's steeper or less steep, rising or falling at different points. Here this curve is steep, the derivative will be a large number. Here this curve is not very steep, the derivative will be a small number, and so on and so forth. Okay, so let's talk about what role does the derivative play in all this. Let's take that same curve I was just talking about up there. Now what you would find is, because the derivative tells you the slope of the curve, for this curve the derivative would be positive from 4 to infinity. Okay, the derivative is positive means that the curve, the function, is increasing or rising. All right, now we saw that already. So on our curve from 4 to forever to the right, it's increasing, it's rising. That translates into the derivative will be positive for any value of x from 4 to infinity. Okay, so derivative positive means the curve is increasing. You'll also find the derivative is negative from negative infinity to 4. The derivative is negative translates into the curve is decreasing. Okay, see our curve right here, or the table, however you want to look at it, from negative infinity over to 4, it's falling, it's decreasing. Okay, the association though is the derivative is negative. Okay, so you associate the derivative being negative to the curve decreasing. Take any x value from negative infinity to 4 and the derivative will be negative for that number. That's because the curve is decreasing. Okay, and then f prime x, the derivative will be 0 at 4 itself. All right, so the derivative is 0 means the curve is horizontal. So as far as slope goes, if a line has a positive slope, it's going up from left to right. That's why the derivative being positive translates to the curve increasing. If a line was falling from left to right, it would have a negative slope. That's why if the derivative is negative, the curve itself will be falling. And then a horizontal line, which is flat, has a slope of 0. So if the derivative is 0, the curve will be flat or horizontal. Now, to imagine that, you'd have to say, like, well, down at the very bottom, it's neither rising nor falling. It's flat. Now, it's a little bit hard to see that. I'll try to do an illustration for you. So let's say imagine that you have, whoops, imagine you have a curve, right? So here's a curve. Then down at the bottom, like if you could imagine me zooming in, like imagine I had a way to like zoom in really close and look just in this box. That's a horizontal line down there. I mean, if you look close enough, it will flatten out. Okay? So at that vertex point at the bottom, where the curve transitions from falling to rising, it flattens out. Okay, so here it's falling, or it's decreasing, but in order to turn around and rise, it's got to like flatten out and then start going up. So we're like right there at the bottom, it's flat, and the derivative is 0 at that point. That point is 4. Okay, all right. So that's why if the derivative is 0 at any particular point, the curve will be horizontal, and that may be a spot where the curve transitions from falling to rising or vice versa. Okay? All right. So next thing, what are critical numbers? Now in this whole analysis of curves and whether they're rising or falling, increasing or decreasing, then there are these things called critical numbers that play a role in that. And I won't tell the whole story right now because we're just getting started, but just to give you the basic definition. So here, definition, what is a critical number? If we get to the point where we're needing to find them. A critical number of a function are just all numbers, all or any numbers where the derivative is either 0 or undefined. Okay? So that's just what a critical number is. We'll explain what role they play in this whole story as we do some examples, but for now, that's what it is. Now on my problem up here with this function, which has this point at the bottom where x is equal to 4, where the curve happens to flatten out horizontally at that point, 4 would be a critical number, because if you found the derivative of this and you put 4 into it, you'd get 0. Well, let's see if that's actually true. Okay, so let's see. Here's that function I was talking about earlier. So the derivative of that is going to be 2x minus 8. Okay, so here's f prime. Here's the derivative. If you plug 4 into that, what happens? 2 times 4, that's 8. Minus 8, that's 0. 4 is a critical number. Critical number is all numbers where the derivative is 0 or undefined. Okay. Now, that's 0. The undefined aspect is a little bit, I mean, we're going to have to see some examples, but let's give some examples just of what's undefined. Okay. You know what we mean by 0, that's probably obvious enough, but undefined, well, here's one that we'll run into. If you have a number divided by 0, that is going to be undefined. Okay, so it might be that the derivative is such that division by 0 is possible, and that would involve a critical number. Okay, all right, so critical numbers either make the derivative 0 or undefined, and as far as it being undefined, that's the scenario that we'll run into. Okay, all right, now let's do an example. Okay, now our examples initially are going to look like this. We'll have a function. Okay, so my function is 12x third minus 27x squared minus 36x plus 8, and I want to determine, like, just by raw numbers, not by looking at the graph, the intervals on which the function is increasing or decreasing. So I want to say, like, if you could see the curve, it would be rising in here, it'd be falling there, and so on. Now, the procedure for determining that, now we'll look at this without the graph. I want to do this analytically. I want to do it just with numbers. The procedure is first determine what the critical numbers are, and second, test the derivative to see if it's positive or negative outside of and in between the critical numbers. That's the procedure for taking a function or a curve's equation and figuring out where it's rising or falling. Okay, so let's try that out. With this function, I want to use this procedure to determine where it's increasing or decreasing. So in order for step 1 to find the critical numbers, I would need to find the derivative and set it equal to 0, right? Because that's what a critical number is. So for my first step, I'm gonna say, okay, well, I need to start by figuring out, can the derivative be 0? All right, so I find the derivative. So I would do like this: 12 times 3x squared minus 27 times 2x minus 36. There's our derivative of this original function. And with a little simplifying, I'll get 36x squared minus 54x minus 36. So there's our derivative. Now I'm going to solve it for 0. I'm going to see if it could be 0. Because at whatever value of x it's 0, that will be a critical number. So I take my derivative, 36x squared minus 54x minus 36, and I set it equal to 0, and I try to solve that. The way I did this is I noticed 18 was a common factor, so I factored out 18. And then this thing, 2x squared minus 3x minus 2, happens to be a quadratic equation. So if I want to solve that for 0, then it's like this. I've got an equation that says ax squared plus bx plus c equals to 0. Okay, and I'm using this. Everybody's seen this before. Maybe you haven't seen it recently, but that's what I'm using. Okay, to solve 2x squared minus 3x minus 2 for 0, I'm going to do the opposite of this number, that's 3, and then b squared minus 4ac, that's going to turn out to be 25 for this one, divided by 2a, that's 4. And then if I reduce that, it's like 3 plus 5 over 4, and then 3 minus 5 over 4, I get 2 and then negative 1/2. Those are my critical numbers, okay? Now, I've offer all the time, I can make videos to review things. If you need, for example, this is just one of many things that I can help you out to review if needed, this quadratic formula for solving a quadratic equation, okay? Now, I explained a little bit about it, but I am taking it for granted that you've seen it before. But if you just don't remember it and you need some help, let me know, okay? Now, nonetheless, I have my critical numbers. So step 1 is complete. Determine the critical numbers for the function, okay? What did it say to do next? Test the derivative for positive and negative values outside of and in between the critical numbers. Now, can you see why that is? If I want to figure out where is a function increasing or decreasing, then, well, it's like if it's increasing, the derivative is positive. If it's decreasing, the derivative is negative. I just need to figure out, like, when is it positive and when is it negative. So here's how I'll do it, okay? I'll set up a little table of test values, and it says choose values outside of and in between the critical numbers. So I found these critical numbers. I found negative 1/2 and 2. So I need to choose some values outside of and in between. It's like I want to test the water at every spot there is. If you imagine, I've got a number line right here. I've got the x-axis. I know that the derivative is 0 when x is 2, and I know that the derivative is 0 when x is negative 1/2. I just need to test a number that is in each spot. So I chose a number left of negative 1/2. I chose negative 1. That's just a test value. You could choose negative 2 or negative 3. Anything left of negative 1/2 could be a test value. For something in the middle here, between negative 1/2 and 2, I chose 0. But you could choose any number you want in between negative 1/2 and 2. And then for a number right of 2, I chose 3. But once again, you can choose anything that you want right of 2. So I put those values of x into the derivative, and I got 54 first. If I put negative 1 in for x in the derivative, I get 54. Now, I don't care that I got 54. I just care that that's positive, okay? Because I'm trying to figure out where the derivative is positive or negative. Because ultimately, I want to answer the question, where's the curve rising or falling? So it's not really that I got 54. I take note that 54 is positive. When I put 0 in, I get negative 36. I don't really care that it's negative 36. I care that it's negative for the purpose of answering our question. When I put 3 in, I got 126. Or again, I don't care that it's 126. I just note that it's a positive number. Now, I got my test values. I'm going to summarize my work over here. if this is the x-axis and I chart what the derivative does along the x-axis, then it would be increasing up until you got to -1/2. Then it would turn around and start decreasing from -1/2 to 2, and then it would turn around again and start increasing on the other side. The curve would look something like this, okay? Where you can imagine -1/2 is right there and 2 is right there. It's rising and falling and rising like that. Okay, that's what this chart in my test values allows me to do. So let's give our answer like this. Okay, so to answer the question of where is the curve increasing versus decreasing, then I'll say this. It's increasing from -infinity to -1/2, but also 2 to infinity. Okay, so let's say that like this. Increasing on -infinity to -1/2 and 2 to infinity. All right, and it's decreasing there in the middle, which is from -1/2 to 2. Okay, so decreasing on -1/2 to 2. Okay, so that's how we would report the answer. Now, these things are intervals, okay? I explained a little bit about that in the beginning of the video, but think about it like this. -infinity to -1/2 just means all values of x from -infinity to -1/2. Think of it like that. This is the portion of the x-axis where the curve is rising from -infinity to -1/2. From 2 to infinity, that's another interval. But from 2 to infinity, that's the part of the x-axis where the curve can seem to be rising also. Okay? All right, so those are called intervals. That's generally how we'll report answers as far as when curves are rising or falling or doing whatever. All right? I just don't want you to think that that's a point. Okay, an interval and a point is something different, but you'll have to use context to figure out what it is. If I put 4, 3, that looks like an interval, right? It's a parentheses, 2 numbers with a comma in the middle, but here it's a point. It means x is 4 and y is 3. Okay, but in the context of me telling you where is a curve rising or falling, increasing or decreasing, you know, -1/2 comma 2 is not a point. It's an interval. It says on the x-axis from -1/2 over to 2, the curve can be seen to be falling or decreasing. Okay, so yes, intervals do look like points, but based on context, you can always figure out if whatever you have is an interval or a point.